really two definitions for us, okay? Definition of a composite function is right here. Basically, the idea is that you're going to plug one function into another. We've been doing this right along. We've done it with several different things. Now we're just going to kind of formally say this is what we're doing. You do want to pay very close attention to this idea of domain of a composite function. Basically, the idea is you look at the domain of the inside function, the function that's plugged inside. Here it's g. Okay, then you form your composite function and you look at your final composite function and see if any other restrictions are necessary. And we'll do several examples and let you see that. The other, let's see, I don't know if there's anything else that I want to show you here in the book. The calculus applications, we will do one of these, but there are other examples here in the book if you want to take a look at them. Yes, let's just go ahead and work some of these problems, okay? So suppose I give you a table, or suppose I give you a couple of graphs, and I tell you to evaluate f circle g of 1. That's what this first thing is saying. This notation right here, you read it f circle g of 1, and it means the same thing as f of g of 1. So you figure out what g of 1 is first, get that y value. That y value becomes the x value for your f function. Okay, so we want to do g of 1 first. Okay, so when x is 1, g of 1 is 0. So g of 1 is 0, and now we need to figure out what f of 0 is. Okay, so when x is 0, f is 5. See how I did that? Okay, let's do it again. Okay, so we want to do g of f of 2. So that's the same thing as g of f of 2, written that way. So I need to plug 2 into f. If I plug 2 into the f function, I get 1 as my answer. So now what I'm really trying to find is g of 1. So if I go to the place on the chart where x is 1, the g value is 0. Okay. See how this is working? Okay, and let's just do one more. G of 1. That bugs some people because it's like, what, g of g? We can do it, no problem. So g of 1. Plug 1 into g, and you get 0. So this becomes g of 0. Go on to the chart where x is 0, the g value is 1. Okay, so there's several of these in the homework. Take your time, practice them. Some are presented like charts like this. Others are presented as graphs where you have to go in and read the y value off the point on the graph, but you can do this. Okay, so suppose I give you two functions and I tell you I want you to find, let's just do all of these. Let's do a f circle g of 4. I prefer to write it as f of g of 4 because that kind of reminds me, it embeds it so I know what I need to do first. I need to plug 4 into g. So I'm going to do that down here on the side. G of 4 is 2 times 4 squared minus 1. So that's 2 times 16 minus 1. 32 minus 1 is 31. Okay, so this becomes f of 31. I'm trying to keep my colors for you. Okay, f of 31 means plug 31 into f. So 3 times 31 plus 2. Okay, that is 95. All right, let's do another. Let's do b. G of f of 2. G of f of 2 means take 2 and plug it into f. So my f function 3 times 2 plus 2, which is 6 plus 2, which is 8. So g of 8 of 2 is what I really need to calculate now. So this is 2 times 8 squared minus 1. So 64 times 2 minus 1 is 127. And I want to go ahead and do the others just so we can practice. Let's see. F of 1. You notice how I'm changing the notation, okay? Again, F circle F of 1 is perfectly fine. I just tend to write it as F of 1. All right, so I need to plug 1 into F. So F of 1 is 3 times 1 plus 2. So 3 plus 1 is 5. So my problem becomes F of 5. So I plug 5 back into F again to get 17. And let's just do one more. G of 0. Okay, so G of 0 is 2 times 0 squared minus 1, which is negative 1. So this becomes G of negative 1. So 2 times negative 1 quantity squared minus 1, which is 2 times 1 minus 1, which is 1. So these are really number crunching if you understand the notation. Okay, so just make sure that this notation doesn't seem weird to you. Okay, all right, let's go here. Okay, now find the domain of the composite function. Okay, so on that chart, on the definition that we looked at in the book, it says, okay, when you want to do the domain of the composite function, you look at the inside function and you figure out what its domain is. So here, F circle G is going to be F of G of X. So the inside function is the G of X. So its domain is restricted from the very, very beginning. So if we look at it, we can tell X better not be 0. Okay, so I'm kind of starting the domain. So all X is such that X had better not be 0. Okay, but notice I'm not going to finish it. I'm not going to put my closing brace, because now what I need to do is I need to actually find the composite function and see if there's anything else that needs to be restricted. Okay, so I'm literally going to find F of G of X. And now this time we're not plugging a number in for X, so the X's are going to be in there. We're going to have to clean this up. We're going to have to keep the fractions. Okay, so the F function is something over something plus 3. These X's I replace with parentheses, because what's going in there is 2 over X, here and here. So, complex fraction, got to clean it up, can't leave it like that. The top is 1 fraction. I'm going to make the bottom 1 fraction. I've got 2 over X plus 3 over 1. So my common denominator is an X. So this fraction needs an X on top and bottom. So 2 over X plus 3X over X is 2 plus 3X over X. So this is where I like to invert and multiply. This is the same thing as 2 over X divided by 2 plus 3X over X, if I want to write it with those symbols, which is the same thing as 2 over X times X over 2 plus 3X. These reduce. 2 over 2 plus 3X. That's F of G of X. Okay. So is there anything else that we need to worry about? Is there any other value that'll make us divide by 0? Take the 2 plus 3x. set it equal to 0. You get 3x equals negative 2. X is negative 2/3. So we'll make that thing equal 0, and we do not want that, okay? So we have to go back up to our domain and say, wait a minute, don't forget negative 2/3 either, okay? So you can't use 0 in the very beginning function in G. So from the very beginning, 0 is out. So then we find our composite, and then we find that we better also throw out negative 2/3 because that also gives us division by 0. Okay. All right, another. Okay, find the domain of the composite function f circle G. So same directions. Okay, again, G is our inside function when it's written this way. So I look over here at G. Do you remember how we find the domain of that? If we're dealing with real numbers here, which is what we're doing, we do not want to end up with a negative number underneath that radical because then we get complex answers. Okay, so we say to ourselves when we're thinking domain, we say x minus 2's got to be bigger than or equal to 0. Because if it's less than 0, then I've got square root of a negative number, and then I have complex numbers, which is not what I want here. Okay, so if x minus 2 has to be bigger than or equal to 0, x has to be bigger than or equal to 2. So I'm going to do the same thing I did with the last problem. I'm going to start it. So it's a set of all the elements x such that x is bigger than or equal to 2. And if you're thinking about it on a number line, if here's 2, we got this. Okay. So that's what we have just when we start. It's very likely we might have to throw out some more of those points. Whenever we have a radical or something where this domain is restricted, to a certain interval of the number line, it's very likely that something else is going to get restricted. Okay, so I've got to find f of g before I can do that. So f of g of x. Let's see. So it's something squared plus 4. Okay. So the something is the square root of x minus 2. Okay. So the square root squared gives me the expression underneath. So x minus 2 plus 4. X plus 2 is the f of g of x. Okay. Now, any restrictions on that? Anything we have to worry about? Division by 0? No radical in that. Okay, so that means actually I was good to go with that domain. Okay, so it did work just fine. Nothing else that needs to be thrown out. The original restriction was enough. Okay, let's do another. Okay, and I picked this one because I want you to see one where it doesn't, where the first restriction is not enough. Okay, let's do A and C on this. Let's do A first. So F circle G, the domain of G well, that's a cute little line, right? That's a linear function. Its domain is all real numbers. So from G, we're cool. We can use anything. So let's go ahead and do our composite and see if we have to restrict anything further. So f is the square root of something minus 2. And the something that we're going to plug in is the g function. Okay. So when we clean this up, we get the square root of 1 minus 2x minus 2. What's that? Minus 1 minus 2x. Okay. So that's our composite function, the square root of negative 1 minus 2x. Now, it's a square root. The stuff underneath, the expression underneath, cannot be negative. So this is going to be restricted. We started with all real numbers. Now we're going to restrict it some. We know that the negative 1 minus 2x has to be bigger than or equal to 0. Okay, so if we subtract 1, if we add 1 to both sides, and then divide both sides by -2, we get x is less than or equal to -1/2. So g wasn't restricted, but f of g of x is. It's restricted to the x's that are less than or equal to -1/2. Okay. Do C for me. Okay. So start in the domain. Okay, F, circle F. So we want, F is our inside function. We come over here, we look, we say, we know that x minus 2 has to be bigger than or equal to 0 because we don't want to take the square root of a negative number. So we know that x has to be bigger than or equal to 2. Okay. So start my domain, all x's such that x is bigger than or equal to 2, but I'm not going to finish it because, again, I might have some issues. I might need to do something more with this. Okay. Make my composite function, f of x. So the square root of something minus 2. What are we plugging in? We're plugging in f, which is the square root of x minus 2. And that is lovely, isn't it? It's the square root of x minus 2, then a minus 2. All right, I'm betting that's going to cause some issues, right? So what do we know? We know that the expression underneath the radical had better not be 0. Okay. Now, be careful with what you do with this. You could think about the transformation on the base graph. You could think about taking the little base graph here and moving it and seeing where it ends up, and then read off the graph where it's above the x-axis. That's a perfectly fine way to work this problem. Okay? The other way to do it is to find the values that make it equal 0, make a sign chart, and test values. Okay? So if I find where it equals 0, add 2 to both sides, square both sides, I get x minus 2 equals 4. Is that right? And then I add 2 to both sides, I get x equals 6. Okay? But that does not finish this in any way. I have to draw my number line. Here's 6. Okay? And then I'm going to test values on each side. But I'm going to remember, up here at the top, my domain was already restricted. So I'm not even going to bother going to the left of 2. I'm going to pick something between 2 and 6. I'm going to pick something bigger than 6. Okay, so let's pick, what, 4? If I pick 4 and I plug it in here, I get the square root of 4 minus 2 is 2 minus 2. The root of 2 is smaller than 2. This will be negative. And you can use your calculator if you're not cool with doing that in your head. That's totally fine. If you pick something bigger than 6, maybe say 7, you get the square root of 7 minus 2 minus 2. So that's the square root of 5. That's bigger than 2 because it's bigger than the square root of 4. So this is positive. Okay? And we specifically want to know where this is bigger than or equal to 0. So that's here. Okay? So our original domain said anything bigger than 2, bigger than or equal to 2. Now we're saying, wait a minute, nope, you can't use anything between 2 and 6. Okay, so we got to come back up here to where we started, and we'll erase that, and this will become all x such that x has to be bigger than or equal to 6. Okay, so I hope that helps. Now these are cool. And if you just think for a second, all right? So think about what we just did. And all they're saying is this is a composite function. What they put together to do it. So if you wanted to do f of g of x and get that, what's f and what's g. Does that make sense? So if you wanted to figure out, you want to get h, f of g of x is supposed to give you h. So what did you plug in and what did you plug it into? Does it make sense to say that f of x is x cubed and g of x is the expression inside the parentheses? Will that work? It's kind of cool, isn't it? Right? Do another one. Come over here. We're seeing that h is is f of g of x. So what was f and what was g that got us that composite function? Do you see it? F could be the absolute value of x, and g could be the expression 2x squared plus 3. Make sure you practice those. They're really cool. They come up again in calculus. Okay. All right. 5.2 has really two things in it, and I pulled the two boxes so we didn't have to flip back to the book. Basically, you have to be able to tell if a function is one-to-one, and you have to be able to find the inverse of a function. And the idea of being one-to-one is the idea that not only does your function pass a vertical line test, but it also must pass a horizontal line test. Okay? So not only does each x go to only one y, each y can match with only one x. So like our birthday example that we used when we first started talking about functions, we said it was okay for for two different people to share the same birthday. When we talk about a one-to-one function, it's not okay for people to share the same birthday. Okay, so no person has two birthdays and no two people share a birthday. So if you're going to find an inverse, you have to have a one-to-one function first, because only a one-to-one function is invertible. So once you have a one-to-one function, then this is the process that they say for finding the inverse. Okay, and I will show you this. This is the actual finding the inverse part. Step 3 is proving that you're right. So you'll see some of the homework problems that just say, hey, here's two functions, prove their inverses of each other. So on those problems, you are really just doing step 3. They're saying we already found the inverse, now you prove we're right. And the notation, instead of where we used g a minute ago, they're using this f to the minus 1 to stand for f inverse, so that we know the two functions we're dealing with. We have one function and its inverse. But notice it's just plugging one into the other. It's plugging f of x into its inverse, and then plugging its inverse into f, and both times you're supposed to get x for your answer. Okay? So that you always have a check to know that you're right. Okay? So the summary from that section, again, is a one-to-one function. It's got to have an inverse. The domain of f becomes the range of its inverse. The range of f becomes the domain of its inverse. Think about it as switching the x's and y's. So if you have a one-to-one function and you have all the points that are on that function, on the inverse, every single one of the x's and y's is going to flip. Okay? So we'll do some examples. And then again, 3 is finding that you've got an inverse and proving that you're right. And 4 here, show that you can graph it. They're invertible over the line y equals x. Okay, so look here. Real quick, these one-to-one or not? So each x goes to only one y, makes it a function. So that's cool. But what messes up the one-to-one is this. It is not okay for two different x's to pair with the same y. Okay? So this is a no. It is not one-to-one. You can't find its inverse. If they give it to you as a set of ordered pairs, well, you're looking to make sure nothing repeats. Now, I mean, I guess they could actually repeat the literal same ordered pair, but we're not supposed to do that when we're writing a roster. So you're literally looking, make sure each x is different, each y is different. And if you go through all of these, that definitely is the case. Yes. That means this is invertible. Okay. All right, so how about we do it? I'll tell you this one's 1 to 1. Okay, you can check it again, but it is 1 to 1. So I can write the domain of this function, right? The domain of this set of ordered pairs are all the x values from the ordered pairs. So what? -2, -1, 0, 1, and 2. And then the range is going to be all the y values, 2, 6, 8, -3, 9. And yes, normally I put them in order, but you don't have to. For this, it's a little bit easier to keep them this way. Okay, so if I wanted to find the inverse, I'd literally switch the x's and the y's. So the point -2, 2 becomes 2, -2. The point -1, 6 becomes 6, -1. The point 0, 8 becomes 8, 0. 1, -3 becomes -3, 1. And 2, 9 becomes 9, 2. Okay. Look at what happens with the domain and range. The domain, 2, 6, 8, -3, 9. The range, -2, -1, 0, 1, 2. So you see what happens? Look. It literally switches the x's and the y's. Okay? The domain of the function becomes the range of its inverse. The range of the function becomes the domain of the inverse. Okay? All right. You can do it with a picture. Suppose we have a graph of a function, and this is what they give us. Okay. Now, they give us this little hint, which we really don't need, where they draw in the line y equals x. We could have put that in there, but they already drew it for us, so we're like, okay, this line is not a part of the graph. The graph itself that we're trying to flip is the blue line. Okay. So, all right, let's see. So the point -2, -2 becomes -2, -2. That doesn't do anything. How about this point? The point 0, -1 becomes -1, 0. The point 1, 0 becomes 0, 1. And the point 2, 1/2 becomes 1/2, 2. Literally switching the x's and the y's. And then sketch it to look like it's flipped across that line y equals x as best you can. And that should have hit here. Okay, so those are kind of cool. You can do those. Let's do, okay, let's do just a couple where we actually find the inverse with the actual function. All right, so find the inverse, check your answer. First, this is a 1-to-1 function. We know what it looks like. We know that its base graph is cube, the cube function. Okay, y equals x cubed. We know it's been shifted up 1, but we know it increases across its domain. We know it's 1-to-1. We're cool. Okay. So the steps for finding the inverse. And I'm going to switch the little blue box I showed you at the beginning. They kept the notation f inverse of x all the way through it. I'm going to use y for a second because it makes it easier. So the steps for finding an inverse. Everywhere you see y, write x. Everywhere you see x, write y. That's what we just did with the other two problems. It works here as well. So if you want to find the inverse, where you see y, write x. Where you see x, write y. And then solve that equation for y. Okay, so I need to move the 1 to the other side by subtraction. And I need to get the y by itself by taking the cubed root. Okay, so I get the cubed root of x minus 1 equals y. And that's the inverse. Okay, that's all you got to do. Switch it back to function notation here, though. So go back to f minus 1 of x is the cubed root of x minus 1. Okay, so literally take your equation. Everywhere you see x, write y. Everywhere you see y, write x. Solve for y, and you got it. Now this check your answer part. That's the part where they want you to do f inverse of f of x and f of f inverse of x. And both times it's supposed to fall out until you get 0. So let's see. Suppose we do f inverse is the pattern. So that's the cubed root of something minus 1. And the something that we're going to plug in, f, is x cubed plus 1. Okay. So this is the cubed root of x cubed plus 1 minus 1 is 0. So this is the cubed root of x cubed, which is x, which is exactly what it's supposed to do. It is not supposed to do anything weird. Okay. Go the other way. Let's see. Let f be the pattern. So it's something cubed plus 1. You're plugging in f inverse of x. So that's the cubed root of x minus 1. Clean it up. The cube root cubed gives you x minus 1 plus 1 plus 1 and minus 1 add to 0 gives you x. Okay? So this is good. We found the inverse and we verified that we did it correctly. That's what this and this does for us. Okay? Do one more problem. I want to show you one with a fraction. Okay? All right, so it is 1 to 1. They tell us in the problem. Okay, so we're going to find the answer. And again, I'm going with the y's. Okay, so where you see y, write x. Where you see x, write y. So x equals 4 over 2 minus y. You got to get the y by itself, so you're going to need to cross multiply. Distribute your x. Okay, now what? Subtract 2x to the other side, so you get minus xy equals minus 2x plus 4. And then you want the y by itself, so divide both sides by negative x. You get y equals, oh, look at those signs. I don't like leaving a minus on the bottom. That's not cool. Are you all right with me saying this is the same thing as 2x minus 4 over x? If I take this negative 1 and I pull it up top and distribute it through the top, I get the 2x minus 4 over x. Okay? This is my inverse. So let me write it right here. So f inverse of x is 2x minus 4 over x. Okay. All right, now we got to do the checking stuff, right? So let's do f of f inverse of x first. So f is 4 over 2 minus something. The something is supposed to be the 2x minus 4 over x. Okay, so you got to get a common denominator. Okay? 2 over 1 minus 2x minus 4 over x. Common denominator is an x. So this is 4 over 2x minus the quantity 2x minus 4 over x. See where this is going? It looks messy to start with, but it's supposed to kind of fall out nicely. So 4 over 2x minus 2x plus 4 over x. That and that add to 0. So this is 4 divided by 4 over x, or 4 times x over 4, which reduces to x. And let's go the other way. You got to do it both ways. So now we need to do f inverse of f of x. Okay. So this time use the 2 times something minus 4 over something as your pattern. Plug in the 4 over 2 minus x and clean it up. Okay, so on the top, I'm going to take a second and rewrite this. 2 over 1 times 4 over 2 minus x is the same thing as 8 over 2 minus x minus 4 over the 4 over 2 minus x. Okay. All I did was multiply this 2 and this 4 together and get 8. So it doesn't look more complicated than it has to be. I need a common denominator. It needs to be a 2 minus x on top and bottom here. So 8 minus 4 times 2 minus x over 2 minus x over the fraction 4 2 minus x. Okay, I am running out of space. 8 minus 8 plus 4x over 2 minus x over 4 over 2 minus x. Sorry. Okay, so what is this? That 8 and that 8 add to 0. So what I have is 4x over 2 minus x divided by 4 over 2 minus x, or times 2 minus x over 4. This and this reduced to 1. 4 and 4 reduced to 1. That's my x that I'm after. Hope this was helpful.